All right. So today is an extension from the lesson we had last, right? So 7.2 kind of goes in hand with 7.3. But with 7.3, we're going to be focusing on the key features and how to graph it a lot more than what we did with 7.2. Okay, so the first thing we need to understand is what rational functions are. Rational functions is basically a fraction. So if you have a number, so if you have a fraction, you can call it a rational function, right? So you're going to have some type of function in the numerator, and you're going to have some type of function in the denominator, okay? So in the numerator, it can be a whole polynomial, or it can just be a number. A lot of the examples we did last class were just where the numerator was just one single number, okay? And then your denominator was some type of polynomial. Now, the second thing we need to bring back from what we've done before is what the degree of a polynomial is, right? So the degree of a polynomial is the term that has the highest power, right? So whichever term has the highest power, that is the degree of the polynomial. And yes, you need to know that specifically for horizontal asymptotes. And same thing for your denominator. You need to be able to look at the polynomial and find the degree of that polynomial. The degree is the term that has the highest power. Now, along with that term, the number in front of it is called a coefficient. But because it's the degree of the polynomial, that coefficient is the leading coefficient. You need that number. So you have to be able to identify that term because it has important information, okay? Now here, I gave you, the second thing is your rational can look all sorts of crazy, okay? So your polynomials don't have to be quadratic. They don't have to be cubic. It can have a power of 10. It can have a power of 100. Like, I don't know. Like, rationals can look really, really crazy, okay? There you go. All right. So right here, I'm just kind of giving you like a basic example, right? So this is your function. This right here, what I just highlighted yellow, that is part of your rational function, right? That is one branch. And then you can see that it's separated, right? And then here we have the second part of your rational function. That's your second branch. They're called branches, okay? So they're separated by a vertical, sometimes a horizontal asymptote, and those are your branches. How do you know how many branches you're gonna have? That's given to you right here. The number of branches is always gonna be the number of vertical asymptotes plus 1, okay? So someone in 6th period asked me to explain that a little bit further because they were confused by it. So here we go. So basically the way I explained it, that helped him understand what in the world I was saying. So if I give you some random curve, right? So here's your function, whatever, okay? If out of nowhere we have a vertical asymptote, what does that mean? It means that I basically just cut that into 2 different pieces. So your branches are how many pieces of this function are you gonna have, okay? So right here, we have a vertical asymptote that essentially cuts this function into 2 different parts. So we have 2 different branches, okay? So that's what that means. Now, the other thing we're gonna talk about is that rational functions can have both vertical and horizontal. Will they always have both of them? No. You can have vertical asymptotes and no horizontals. You can have horizontals without verticals. You can have different combinations, but you can also have both, okay? So for this basic example, I'm giving you both. I gave you a vertical asymptote and a horizontal asymptote because this is similar to your parent function. Now, your domain. Notice that for your domain, I didn't give you a specific number the way I normally do, right? Because it changes. How does it change? It's always going to be all real number except your wholes and your vertical asymptotes, okay? So your domain is not that hard in comparison to your range. Your domain is all real numbers except wherever you have wholes and vertical asymptotes. Now your range, you're gonna see that I wrote determined through analysis of the graph. because it's not that easy. Why is it a little bit more difficult? What makes it a little bit more difficult is the horizontal asymptotes. Because from last class, we talked about horizontal asymptotes and how they differ from vertical ones. Vertical asymptotes will not get crossed, right? If you have a vertical line, you know that line will never get crossed by the function. But if you have a horizontal asymptote, it is possible for the horizontal asymptote to get crossed somewhere in the middle, but the ending behavior of it will not, okay? And you will see an example of that here in a minute, and we will talk about that. Okay, now, right here, I kind of gave you like a mini looking chart or whatever, steps on how to find, I would say the most important new key features, right? You should already know how to find x-intercepts, and you should already know how to find y-intercepts. I will give you a quick review on that when we get to the examples, but you should know how to find that by now, no matter what function I give you, okay? I get it's rational and it's still a little new, which is why I'm gonna review on how to do that real quick, okay? But for your holes, you will see that I drew a little shovel with some dirt and a hole. What is a hole? A hole means that I removed something in order for there to be something missing, right? So that is why in the last class, remember, I kept making y'all write no holes because nothing canceled out. Nothing was removed. Nothing was simplified. Okay, so what by that I mean, this is how I remembered what holes were when I was in high school. It's because if I canceled it out, that means that I am removing this from the rational function the way you remove dirt from the ground. So it is a hole. You're missing that now, okay? So how do we know we have a hole? Because you were going to physically remove something, and I will show you what that looks like, okay? So right below that, right here, you can see that this would be the original problem, right? What I highlighted purple. So this would be the original problem. When I factor it out, you can see that you have x minus 3 and x minus 3. Do you see how those are matching, right? So what does that mean? That means that you're going to divide the factor x minus 3 divided by x minus 3. So what does that do? They cancel each other out. Because you can cross them out and remove them, right? They simplify to 1. X minus 3 divided by x minus 3 is 1, right? So it's removed, it's simplified. Then I know that that's going to be a hole. How do I find it? The thing that you just canceled out, you're going to set it equal to 0 and then solve. That is your hole. That is how we find holes. If it cancels out, set it equal to 0 and find your hole. Now, once you find your holes, then you can find your vertical asymptotes. So this is the only thing that has to be done before you can find a VA, right? You have to find the holes first and then vertical asymptote. After you find your holes, all you have to do is set your denominator, whatever is left over, right? So you can see that I use the exact same example here. And you can see that my holes is what canceled out, right? So you end up with this. This bottom part is what's remaining. So what did we do? We set it equal to 0 and then solved. So that is where your vertical asymptote will exist, okay? Then for the last key feature that we talk about here is horizontal asymptote. Okay, well, what are these? Now, this is the one that's a little annoying because it has different cases, okay? So right here, the first thing you need to be able to do is identify the degree of the numerator and the degree of the denominator and the leading coefficients. If your numerator, so you can see right here, I wrote numerator on the left and then denominator on the right. So if your numerator is bigger than the denominator, and we're talking about the exponents, right? So don't forget that we're talking about exponents here. If your numerator is bigger than the denominator, then you have no horizontal asymptote, which means you have a, what's that called? A slanted asymptote. Okay, and there's one example that has one. I will do it just so that y'all can see what that would look like. Now, if your numerator is less than the denominator, then your asymptote is automatically at y equals 0. And if your if the degrees of the polynomials are the same in both the numerator and denominator, then your horizontal asymptote is always going to be the leading coefficient, so a divided by b, and then simplify, whatever that may be, okay? So the leading coefficients, okay? And then down here, I kind of give you an example of each one, right? So in this first one, your numerator is 3 and your denominator is 2. So 3 is greater than 2, so you have no horizontal asymptote, which means we have a slanted asymptote. For the second one, we have 2 on the top and 3 at the bottom. The top is smaller than the bottom, so your horizontal asymptote is at y equals 0. On the last one, you can see that the degrees of each polynomial are equal to each other. So your horizontal asymptote is the numbers in front. So 2 over 3, that is simplest form. So your horizontal asymptote is at 2 over 3. Okay, okay. All right, so that is all the information that's given here. This will help you go back in case you forget how to do something, yada, yada. Okay, now, so example 1. Now, determine the horizontal and vertical asymptotes, the number of branches, the domain and range, and we're also going to find the holes, but I accidentally left that out, okay? So for example 1, again, you can kind of sort of find these features in whatever order you want. The only one that is very particular is holes and vertical asymptotes. If you're going to find your vertical asymptotes, you have to find the holes first. Those are the only two that have to go together. I'm going to do horizontal asymptotes first, just because it's already in standard form. And to find the degree of the polynomial, that's really easy. All I have to do is look at the terms, right? So let's start with horizontal asymptote. So our horizontal asymptote, that's what we're going to find first. Okay. So we're going to look at our numerator, and the degree of the numerator is what? What is the highest exponent we have? Thank you, Edie. It is 2. So the degree of the numerator is 2. What about the denominator? What would be the degree of the denominator? Two. Okay. And I know that because it has the highest power, right? This one's a 1, and that 5 is 0, right? X to the power of 0 is 1. Okay. So what do we see here? We see that our degrees are equal to each other. So because they're equal to each other, what does that tell me? So if I go back to my notes, that means that my horizontal asymptote is going to be my leading coefficient. So 2 equals 2. So then that means we're going to look at the leading coefficient. So the leading coefficients here would be 1 and 1. So then y, remember, horizontal is hoi, right? So that's how I know it has to be y. So y equals 1. So your horizontal asymptote would be at y equals 1 because your degrees are the same. The next thing we're going to look for is going to be your holes / vertical asymptotes. Now remember, in order to do your holes in your vertical asymptotes, you have to factor first. Okay, so let me go ahead and rewrite it. So we have x squared minus 4 over x squared plus 4x minus 5. So your numerator, hopefully you realize that your numerator is difference of squares. And in case you forgot what difference of squares was, difference of squares. We did this first semester. And remember, I told y'all need to remember how to factor, right? So a squared minus b squared, automatically you can put it in factor form as a plus b, a minus b. And the reason we can do that is because I see a minus. X and 4 are both perfect squares, right? X times x is x squared and 2 times 2 is 4. So they're perfect squares. So my numerator is going to be x plus 2, x minus 2. For our denominator, you're actually going to have to put some work, right? So remember, on the top is a times b, which is -5, and in the bottom, is going to be your b, which is 4. A times b, what's wrong with me? A times c, which is 1 times -5, and then in the bottom it's going to be your 4. So what two numbers multiply to -5 but add to 4? The only factors of 5 are 1 and 5, right? So we have 1 and 5. So when I multiply these, it needs to be a negative. So I know one of them has to be negative. And to get a 4, the bigger number has to be positive. So it's -1 and +5. So then we're going to have x minus 1, x plus 5. Because my a is 1, that's it, I'm done. There is no more simplifying, right? If I divide by 1, it's not going to change anything, so I'm done. So now that we have it in factor form, we're going to check, can I cancel anything out? By that, I mean, do I have any matching factors in the numerator and the denominator? So does anything match? Does it? So look at this example above I gave you. These match. Why do they match? They match because this is x minus 3, x minus 3. They match, right? It's like a matching game from like elementary, right? If they look exactly the same, you know they match. So if you're looking at this example, right? X plus 2, x minus 2, it's in my numerator. And then in my denominator, I have x minus 1, x plus 5. Do any of them match? No. So because none of them match, then I know my holes are none. And once we see an example where you do have holes, that'll make more sense. Okay, so that's coming. So then for your vertical asymptotes, that means that whatever's remaining in your denominator is going to get set equal to 0. So in our denominator, right, we have x minus 1, and then we have x plus 5. And we're going to use zero product property. Why? Because we do not want the denominator to be 0. If the denominator is 0, it is undefined. So we cannot have that. That's where vertical asymptotes come from. Okay. So we're going to have x minus 1 equals 0, x plus 5 equals 0, and solve for x. So x cannot equal +1, and x cannot equal -5. If we plug in 1, 1 minus 1 is 0, right? Well, what's 0 times the second number? 0. If x is -5 and we plug in -5, -5 plus 5 is 0. What's 0 times the first number? 0. The denominator cannot be 0, and we've talked about that a few times, right? The denominator can't be 0. That's where vertical asymptotes come from. So your vertical asymptotes are at 1 and -5. So we have found the holes, which are none, and then the vertical asymptotes. Okay. So then now, what are we still missing? The number of branches. The number of branches comes from vertical asymptotes. We have two asymptotes, so 2VA plus 1 is going to be 3 branches. So we're going to have 3 branches, which means we're going to have 3 sections to this function. Okay, last thing we need to identify is the domain and range. So the domain and range for this function, let me draw a line there. Okay, so our domain is the easier one. Your domain is always going to be all real numbers except your wholes and vertical asymptotes. So your domain is X, where X is an element, and that E means element. It means it's a part of something. What is it a part of? It's a part of all real numbers. And if you remember, all real numbers can be written as an R with the line in the middle of it. That means all real numbers, because someone asked me last period, so I'm explaining it again now. So all real numbers, except, so we're going to put a comma. There's no hole, so we don't have to worry about that. X cannot equal 1 and X cannot equal -5. Oh, I wish I would have written that. Here, hold on. Let me write it differently. Okay. X cannot equal 1 or -5. There we go. Okay. There we go. Okay. Now, for your range, this is where it gets a little bit more tricky. It's always better to graph it and look at the analysis in order to properly determine what the range is. Because again, last class, we talked about how you can have a horizontal asymptote, but you can cross a horizontal asymptote, right? So let's go on ahead, and I've already graphed it actually. So let me turn this off. So this one right here, oh wait, where's the other one? Okay, so right here, we can see that we have our vertical asymptote, which is -5, and then 1, and then we have a horizontal asymptote at 1. Does everyone see that? Okay, but here's what's interesting. We can see that our domain, right? We can see -5 right here, and we can see this 1, right? That represents my asymptotes. Do you see how the red lines will never touch those 2 vertical lines, right? That is why your domain is excluding those points. But if you look at the range, right? What is range? Range is bottom to top. Going from the bottom, obviously, all of these points matter, right? So do we look at the Y values, -9, -8, -7? I can keep going and going and going, right? But once I get to the Y, to the horizontal asymptote at Y equals 1, do we see how in the middle, it actually equals the horizontal asymptote here, right? Do we see that? But if I look at this side and I keep going and going and going and going and going and going and going, I wonder if it'll move, right? If I zoom in, so if I go all the way to the right, so let's go to some crazy number, like 1,000 over here, right? You see how it looks like it's merging into the red line? The red and purple look like 1, right? But if you zoom in close enough, you're gonna see that there's always gonna be space between them. Why? Because that's what's happening at the ending behavior of the horizontal asymptote. As you approach positive and negative infinity, it will look like they merge into each other, but they will never be 1. They will never equal each other. They will never touch each other at the end of it. But if you look at the middle, stuff can happen in the middle. So because it actually equals 1 right there, 1 is part of your range. So your range for this problem is going to be all real numbers, even though you have a horizontal asymptote. Okay, so your range is going to be Y such that Y is an element of all real numbers. Okay, yes, we have a horizontal asymptote. I know that, we see it, we understand it's there, but a horizontal asymptote only explains the ending behavior of a graph as it approaches negative infinity and positive infinity. It does not mean that it does not cross in the middle. Okay, so that's the number one thing I wanted to talk about for that, okay, because it does equal 1. So don't be getting it twisted. Okay, example 2. Okay, for example 2, same thing. I'm going to go on ahead and start with the horizontal asymptotes, right? So in order to do the horizontal asymptotes, I'm going to look at my degree of each polynomial in the numerator and denominator. So in my numerator, what would be the degree of the polynomial? If you remember laws of exponents, x to the power of 0 is always equal to 1, right? So the degree of the polynomial in the top is 0 because there's no variables. And the reason there's no variables is because that variable has a power of 0, which makes it 1. So then the degree in the denominator is going to be 2. So here we have the degree of the numerator is 0, which is smaller than the degree in the denominator, which is 2. So we have a less than symbol. So if we go to our notes, we can see that our horizontal asymptote would be at 0. So our horizontal asymptote is at y equals 0. Next, we're going to want to find wholes and vertical asymptotes. Now, remember, in order to find wholes and vertical asymptotes, we have to factor. For our numerator, there's nothing to factor, it's just a 1. For our denominator, we have x squared plus 2. This is not difference of squares because we have a plus, not a minus, and 2 is not a perfect square, right? So it's already simplified. I can't simplify it any further. Okay, so in order to, so for wholes, we don't have any because there's nothing to cancel out, none. For our vertical asymptotes, right? So vertical asymptotes, we're going to grab our denominator, which is x squared plus 2, and set it equal to 0 and solve. So we're going to subtract 2 to both sides. So x squared equals -2. But if I take the square root of x squared, I cannot square root a negative number. What does that mean? That means that we have no vertical asymptotes. Why? Why do we not have any? Because your denominator cannot physically be 0. Remember, we find vertical asymptotes because we do not want the denominator to be 0. But here we have x squared plus 2. So it does not matter what number I put in there, we will never get a 0 out of it, ever, ever, ever. Okay, so that is why there is no vertical asymptote. Okay, so there's no vertical asymptotes for this problem. Now, okay, so then number of branches. Remember, basically that means how many sections is this rational going to be cut up into, right? Because there's no vertical asymptotes, then that just means I'm going to have one big chunk. So we have one branch. Now, for our domain is easy. It's going to be all real numbers except your wholes and vertical asymptotes. We don't have any wholes and we don't have any vertical asymptotes. So your domain is actually going to be x, where x is an element of all real numbers. And this is not the only way to say that, right? There's different ways of saying that. I can say just x. That's also the same as saying all real numbers, any value. Yeah, anyway. Now, range. Your range for this one, because we have a horizontal asymptote at 0 and we have one branch, then it would be easier if I just showed you what it looked like. Okay, so for example 2, right, let me turn this one off, which is this one right here. Okay, so do y'all see how we have a horizontal asymptote at 0, right? Y equals 0. It's basically the x-axis, right? Same thing. Do y'all see how it looks like that green line is on top of the x-axis? right? Which is y equals 0. So I can go down again all the way to like 1,000. It doesn't freaking matter, right? If I zoom in close enough, you're always going to see that there's always going to be space left in between. Okay. So the ending behavior of this graph, right? There's a horizontal asymptote there. So we end up back here. You can see that it's one branch. So what is your range? Your graph exists in between 0 and 1. Oh, I told 6th period wrong. I just realized that. Oops. We can see that we have like a little maximum there, right? And it's not going to go above 0.5. So not even 1. It would be 0.5. So then your range is actually from 0 all the way to 0.5. It's not going to equal 0, but it can equal 0.5. The other way you can write this is an interval notation, right? So it would be open 0, comma, 0.5 closed. Oops. I'll explain this to 6th period tomorrow or the next time I see them. My bad. Okay. Example 3. Okay. What would my horizontal asymptote be? How do I find that? We've done a few examples. So to find horizontal asymptotes, what do I need to do? Edie's, you're on it today. So you need to find the degree of your polynomial. Daniel, what's the degree of my numerator? Ramon, what's the degree of my denominator? 2. So for my horizontal asymptote, we have 2 equals 2. So when they're equal to each other, all you're going to do is look at the leading coefficient. Your leading coefficients for both of them is 1. So what's 1 divided by 1? So your horizontal asymptote is at 1, y equals 1. Whatever your leading coefficients are. And that's given to you in your notes, right? Okay. Now, we can move on to our holes and vertical asymptotes. Now remember, in order for us to do our holes and our vertical asymptotes, we have to factor first, okay? So first, we're gonna, and before we can do this, I need a factor. So we're gonna factor the numerator, which is x squared minus 3x plus 2. How do we factor? We're gonna set up our little diamond. This is 1, so 1 times 2 is 2, at the bottom -3. So what numbers are gonna go here? What numbers will multiply to 2 and add up to -3? Yes, almost. It would be a -1 and a -2, right? -1 times -2 is a +2. If you add them together, it's a -3. So -1 and -2. So that means that these numbers I'm going to write in factor form. So x minus 1, x minus 2. Divide by a. My a is 1. But if I divide by 1, it's not going to change anything, right? So then your factor form for the numerator is going to be, where should I write that up? Right, I guess here. X minus 1 times x minus 2. Now, we're gonna go do the denominator. So for our denominator, we have x squared minus 6x plus 8. Remember I told y'all last class, you need to remember how to factor, right? I was in line. So we're going to go on ahead. Remember, at the top is a times c. So this is 1 times 8, which is 8. And at the bottom is -6, which is always going to be your b. What two numbers are going to give me 8 when I multiply, but when I add them, it's -6? Yep, -2 and -4. -2 times -4 is 8. -2 plus -4 is -6. So we can now put this in factor form. So we're going to have x minus 2, x minus 4. When we divide by a, which is 1, it's not going to change anything. So we're going to have x minus 4, x minus 2. Okay, so now that we have it in factor form, now we can do the whole. Okay, so where are my wholes going to be? Well, do we have factors that match? Look at your numerator and look at your denominator. Do you see any factors that match, that are the same? X minus 2. Does everyone see that these match, right? So what does that mean? That means that x minus 2 divided by x minus 2 is 1, so these cancel each other out. So to find our wholes, we're going to grab this, what we canceled out, and set it equal to 0 and solve for x. So add 2 to both sides. X cannot equal 2. You're going to have a whole there. And literally what it sounds like, that's exactly what it is, right? So when you graph it at that point, you're literally going to see an open dot, like a little hole. So for your whole, you're going to have one at x cannot equal 2. So now for your vertical asymptote, right? So we just found our whole. So for your vertical asymptote, you're going to grab what you have left, which is x minus 1 over x minus 6. Whatever's left in the denominator, you're going to set that equal to 0. So we have a vertical asymptote at 6. So x cannot equal 6. So your vertical asymptote is that x cannot equal 6. Why? Remember, if you plug in that 6, 6 minus 6 is 0, and 0 times any number is always 0, and that cannot happen in the denominator. That is why we have a vertical asymptote there. What else am I missing? Okay, so when you have we have one vertical asymptote, so that means that the number of branches is just going to be 1 plus how many you have. So we're going to have 2 branches. Okay, so your domain for this function is going to be x is an element of all real numbers except your wholes. So x cannot equal 2 and it cannot equal 6. Your wholes and your vertical asymptote. So your domain is all real numbers except 2 and 6. Because we have a whole and an asymptote there. So it cannot equal those two. Okay, and then for your range, this is where graphing it would just help us a lot more. So your range, let me see, this was example 3, which is this one. So we can see that you can kind of tell that there's a horizontal asymptote right here at 1, right? Which is what we had. So for this rational function, we can see that it's never going to cross the horizontal asymptote, but it goes down infinity and then it goes up infinity. So your range for this problem is going to be all real numbers except where y is equal to 1. So y cannot equal 1. So range is y, where y is an element of all real numbers except y cannot equal 1, which was our horizontal asymptote. So really for your range, you just have to figure out, is it going to cross your horizontal asymptote or not? If it crosses it, then it doesn't matter that it's an asymptote, it's still going to be part of the range because it touches it at least one time. If it doesn't touch it at all, then you exclude it. It's not part of the range. Okay, example 4. Okay, so we're gonna start off by finding our horizontal asymptote again first, right? Because to me, it's already like expanded, so it's easy to find the degree of the polynomial. Okay, so the degree in the numerator is what, Getsemani? The degree of the polynomial in the numerator, what is it? 2. And then the degree of the denominator is what, Diego? Huh? It's only 0 if there isn't a variable. So you see this one right here, where it was 1 at the top, right? So because there's no variable, then that's when the power would be 0. But because you have an x, that means that the power is 1. So the degree would be 1 in the bottom, okay? So then now that we know our degrees for a horizontal asymptote, because 2 is greater than 1, right? So when 2 is greater than 1, if you come up here to your notes, I give that to you. If 2 is greater than 1, then that means there's no horizontal asymptote, but there's a slanted asymptote, okay? So there's no horizontal asymptote, none, right? Because the degree is bigger at the top than the bottom. There's no horizontal asymptote, but there is a slanted asymptote. Now, do we involve slanted asymptotes in your exam? I don't think so. We already made it. I'm pretty sure there's no slanted asymptotes, but I'm still going to show you how to find it, okay? Just so that you're exposed to it, okay? So to find a slanted asymptote, divide. You're going to divide, and your quotient is your asymptote. Okay, so I'm gonna just do that real quick for y'all. I did it on the side for 6th period. Okay, so if I wanted to find the slanted asymptote, then I'm gonna divide this function, right? So we're gonna have x squared plus 2x minus 3 divided by negative 3x minus 6. Remember when we did this in first semester? Okay, so negative 3 times what is going to give me x squared, okay? This is a 1, right? So negative 3 times what is going to give me a 1? The only thing that can give me a 1 is its inverse. So negative 3 times negative 1 over 3. Why did I pick that? Because negative and a negative is a positive, and 3 over 1 times 1 over 3 is 3 over 3, which is 1, right? Which is what I want. So then I'm going to do negative 1 over 3, and I have 1x, but I need 2, so that's going to be negative 1 over 3x. After I find that top number, I'm going to multiply, right? Negative 1 over 3x times negative 3x is going to be a positive x squared. And if you remember when we did division, that first term has to match, which they do. Then we're going to multiply negative 1 over 3x times negative 6, which is going to be a positive 2x. What do we do after this? We subtract. X squared minus x squared is 0. 2x minus 2x is 0. So we are left with a -3. Negative 3x does not go into -3, which means that this is my remainder. This, I don't care about this. So this right here is all I need. So my slant asymptote is gonna be at y equals -1/3x, by the way. Okay, so that's how you would do that. Do not stress yourself out. What's important for you to understand today is how to find your horizontal, vertical asymptotes, and your holes. That is the main thing I need you to worry about. I showed you how to do that just so that you've seen it, you're exposed to it. So if you take pre-cal and y'all have to do it, at least you have some type of memory of seeing it before, okay? You know how to divide. I've already taught you how to do that. That's how you would find that, okay? And then I'll show you right now that I'm right. Okay, so there's our horizontal asymptote. We don't have any, which means I have a slanted asymptote at y equals -1/3x, right? So then now I'm gonna find my holes and vertical asymptote. So to save time, I'm just gonna give you the factored form already. So the factored form would be x plus 3, x minus 1 over -3, x plus 2. So we can see that we don't have any holes. So holes are none. We don't have any, right? So then for our vertical asymptote, all we have to do is grab what's left in the denominator, -3, x plus 2, and set it equal to 0. So divide by -3 to both sides, we have x plus 2 equals 0. And then subtract 2 to both sides, so x equals -2. So you have a vertical asymptote at x equals -2. So number of branches would be your vertical asymptotes plus 1. We have 1 vertical asymptote, so we're going to have 2 branches. So your domain, let me do this in a different color. Your domain is going to be x, where x is an element of all real numbers except your holes and your vertical asymptotes. We don't have holes, and my vertical asymptote is at -2. So this is your domain. And then your range is going to be, well, we're going to have to go look at the graph of it, right? So the only thing that's questioned here is your horizontal asymptote. We don't have a horizontal asymptote. So more than likely, our range is going to be all real numbers. But we're going to go look at the graph so that we can visually see that, okay? So your graph, so this is the one we just did, right? So do y'all see how there's no horizontal asymptote, right? It's not merging into a straight horizontal line anywhere. But what you can see is that there's like, so here's the slanted asymptote I found, right? This one right here, that red line. So do y'all see how the black looks like it's gonna merge into the red? That red line that's there, that's the horizontal asymptote I found a minute ago, right? When I divided and I got my quotient, that's my slanted asymptote. So it's basically a linear function, okay? So you see as I zoom out, it looks like it's gonna merge into it, right? But if I zoom close enough, you're gonna see that there's always gonna be space between them, no matter how far out I go, okay? So there you go. So then what do we know about our range? Our range, if I'm here and I drag this dot, do you see how there's a number everywhere? Right? I go here and I have a number everywhere. Same thing if I come this way. If I come down, I have a Y value at every spot. It doesn't matter that I have a slanted asymptote because every Y value is being covered. So that means that my range is all real numbers. So your range is Y, where Y is always an element of the reals. Wasn't that fun? Now we're gonna go graph it. Here, I'll let y'all write that down real quick. Sorry. Now we're gonna go graph these. Ooh, ow. Okay. All right. So for example 5, this is an easy one because my numerator is not a polynomial, it's just a constant, right? So let's start with the horizontal asymptote. Okay, so for the horizontal asymptote, what is my degree of my numerator? Zero. Okay, so this one, the degree of the numerator is 0. What about the degree of the denominator? 1. So that means that the degree of my numerator, right? So let me write numerator, denominator. Numerator is 0, denominator is 1, and 0 is smaller than 1. So what does that mean? That means that my horizontal asymptote is at y equals 0. Okay, and I can see that from the notes. So y equals 0. So this is my horizontal asymptote. Next, we're gonna go find our holes and then our vertical asymptotes, right? So holes always goes first. Well, we already have it simplified. It's already simplified. I can't factor anything out. Since I can't factor anything out and nothing is cancelable, I don't even know if that's a real word, but nothing can reduce, right? So that means that we don't have any. There is no holes, none. So for your vertical asymptote, we're gonna grab our denominator and set it equal to 0. So x cannot equal a positive 5. So we have a vertical asymptote at x equals 5, which means we're going to have 2 branches. Because I only have one asymptote that's vertical, I just add one more, so I have 2 branches. I know that for sure. Now, this is where I told you that you should remember how to find x-intercepts and y-intercepts. So I'm going to tell you. So for your x-intercepts, you're going to set the numerator equal to 0 and solve. And for your y-intercept, you're going to plug x equals 0 and solve for y. Okay, in case you forgot. So here we go. So for this one, for your x-intercept, right, our numerator is 4, set 4 equal to 0. That does not happen. So there is no x-intercept. That means this graph will never cross the x-axis. So that tells me that my horizontal asymptote is at y equals 0, right? So I know I have, here, we'll graph it in a minute. Now, for your y-intercept, right? So for our y-intercept, I'm just gonna plug in 0 in for x. So you can grab the function and just plug in 0. So 4 over negative 5. So your y-intercept is at negative 4 over 5. Okay, so let's start doing this. So our horizontal asymptote is at y equals 0. 0's in the middle, so here's my horizontal asymptote. So here's your HA at y equals 0. Then we're gonna do, we don't have any holes. My vertical asymptote is at negative 5. So I'm gonna come over here to where negative 5 is at, which would be about right here. And I'm gonna draw a vertical line at negative 5. So here's your vertical asymptote at x equals negative 5, or yeah, negative 5. Or wait, was it negative 5 or positive 5? Oh no, it was positive 5, my bad. Sorry, it was at positive 5, which would be about here, my bad. Okay, here we go. Okay, so This is a vertical line, x equals 5, right? Which is our vertical asymptote. So now to graph this, I need my key features, right? So x-intercept, we don't have any, which tells me that it's not going to touch the x-axis or cross it, nothing. So your y-intercept is at 4, -5. 4 over 5, I'm sorry, 4 over -5. Ay, Dios mío, ya ni puedo hablar. -4 over 5. Sorry. So this is -1. So -4 over 5 would be right above that. So I know I have a y-intercept here, which tells me that my graph has to get close to that asymptote, cross my y-axis, and then get close to this asymptote. So there's that part. And because this is a rational function, I know that this is going to be across from there. So then we're going to go this way. Or you could pick an x value and plot it, right? So if I picked 6, x is 6. So here's 6. 6 minus 5 is 1. So 4 over 1 is 4. So 6, 4. So this is probably right there. You could literally, but I mean, really the important thing here is being able to graph your horizontal and vertical asymptotes and your holes. That is my main priority. And figuring out where the rest of the branches go, right? And we have 2 branches, which is exactly what we said here. Okay, number 6. To save time, I'm going to go on ahead and give you the factored form of this. So your factored form of this would be x plus 2, x plus 1 over x plus 2, x minus 1. Okay, so for a horizontal asymptote, remember, we want the degrees of the numerator and then the degrees of the denominator, right? I should have done this in black. So the degree of the numerator, what's the degree of my numerator? Look at the original problem, x squared plus 3x plus 2. And then my denominator, what's the degree of my denominator? So that means that we have 2 equals 2. So then all I'm going to do is grab my leading coefficient, which is 1 over 1. So my horizontal asymptote is at 1. So I know that I'm going to have a horizontal asymptote at y equals 1. So there's that. Here's 1. So y equals 1. Now we can go find my holes. Okay, so looking at the factor form, do I have any holes? Do I have any holes? How do I know if I have a hole? What am I looking for? How do I know if I have a hole? Go look at your notes in the front. How do I know if I have a hole? Oops. So does everyone see how these are matching? Right? X plus 2 divided by x plus 2. These cancel each other out, right? So your hole is going to be wherever you had a cancel, set it equal to 0. So x cannot equal -2. Good job, Edie. X cannot equal -2. So you have a hole at x equals -2. So on your graph, here's -1, -2. You have a hole right there. I have an open dot. Literally, that's it. That is what you just found. You have a point of discontinuity. That means that you're, for a split second, you're discontinuous there. So then now to find your vertical asymptote, right? We're gonna grab what's left, and what's left is x plus 1 over x minus 1. You're gonna grab your denominator and set it equal to 0. So x minus 1 equals 0. So vertical asymptote, denominator equals 0. So x cannot equal a positive 1. So your vertical asymptote is at x equals 1. So here's 1 over here. We have a vertical asymptote at this. So here's your VA at x equals 1, vertical line, and you have an HA at y equals 1. So what does this mean? Number of branches, because we only have one vertical asymptote, is 2. So we have 2 branches. So we're going to find our x-intercepts. To find our x-intercept, we're going to set the numerator equal to 0, which is x plus 1 equals 0. So your x-intercept is at -1. So at -1, which is right here, I'm going to have an x-intercept. So this is a closed dot, and at -2, we have an open dot. For your y-intercept, all you have to do is plug in x equals 0 and then solve for y. So you can grab the original function or you can grab the simplified one, right? X plus 1 over x minus 1. So that's going to be 0 plus 1 over 0 minus 1, which is 1 over -1. So your y-intercept equals -1. So here's -1 right about there, and you have a y-intercept. So that can kind of tell you where one of your branches is going to be. So you're going to have a branch that's going to get really close to your horizontal asymptote. I did do this right? Yeah, I did. Okay. Sorry, hold on. Let me do that again. So it's going to go like that, and then like that. And then if you wanted to find where the other branch is going to be at, just choose an x value and plug it in. But because it's a rational function, I know that if it's in this section, it has to be in this section. So it's going to go like that. And if you plug any point in that's over here after +1, that point is going to land in this section right there where I did that P, the second branch. Well, if I wanted to find the whole, yeah, that's right. Okay. Anyway, okay, so for example 7, we already did example 7. It was the very first one we did. So I'm just going to write all of the key features down, and then we're going to find the x and y intercepts and then find it and talk about it. Okay, so our holes, so example 7 was example 1, right? All of the key features were here. We already found all of them. We found the holes, which we didn't have any. We found the vertical asymptote, we found the horizontal asymptote, and we knew that we had 3 branches. So all of that information I'm going to write down here because we already found it. So the factor form of this was x plus 2, x minus 2 over x plus 5, x minus 1. Okay, so holes, none. Vertical asymptote was that x cannot equal -5 and x cannot equal 1. And then we have the horizontal asymptote was at y equals 1. And then so we have 3 branches because of the vertical asymptotes. And I think that's it in that part. Okay, So then let's go on ahead and graph what we have. So we have a horizontal asymptote at y equals 1. So let's make this one right here. Okay. And we have vertical asymptotes at -5, which would be about here. And then at 1, which would be about here. So this is -5, this is 1, and then this is 1. Okay. So we have all of our asymptotes done. Now, in order to figure out where my branches are going to go, I need to find my x-intercepts and my y-intercepts. So x-intercepts are done by setting the numerator equal to 0. So x plus 2 equals 0, x minus 2 is equal to 0. So x equals -2 and x equals 2. So we have 2 x-intercepts at -2, which is going to be about right here. Let's put a dot there. And then at 2, which is about here. So let's put a dot there. So I can already see that we're going to have something's probably going to cross. Now for our y-intercept, all we have to do is find f of 0. So you can do that from the factored form, or you can do it from the original. So I'm going to put 0 squared minus 4 over 0 squared plus 4 times 0 minus 5. So 0 squared minus 4 is -4. 0 squared, and that's 0, right? So we end up with -5. So my y-intercept is at positive 4 over 5. 4 over 5 is right below 1. So we're going to have a y-intercept right there. Okay, so looking at the dots, this is where you're just gonna, you kind of have to see what's going on, right? So we have these 2 dots right here. So we know these are going to be connected. And I have asymptotes. Why are asymptotes special? Because it's telling me that my graph is going to get really, really close to them, but it's never going to cross for vertical asymptotes. So I know that I'm going to go this way, get really close, but never touch. And then I have to do the same thing, but with the asymptote on the right, get really close, but never touch. And if you wanted to be more sure of that and be like, well, miss, how do you know it's not going anywhere else? Then just plot another point, right? If you put, let's say 0.5 in the function, 0.5 squared minus 4 divided by 0.5 squared plus 4 times 0.5 minus 5, you would get a y value and you could graph it. I'm not going to do that right now because this is what it's going to look like, okay? All right. Then you can see that you have an x-intercept over here. So that means that this is going to look something like that because it has to approach your asymptotes. So if we have that there, then that means that my third branch, remember we have 3 branches, my third branch is going to be somewhere over here. And then ta-da, that is what your graph would look like. Let me box vertical asymptote. We have no holes, y equals 1, your y-intercept, your x-intercept, okay. And then ta-da! Questions, comments, or concerns? Okay,